Hello. Um, it's me, Keith again. This is for those who missed the class that we had today at Thursday at lunch. It's going to be at Thursday at lunch every day from now on. Or for those who want to return to the lesson today because it was a little bit confusing in class, I feel. So if you want to return to it, that's fine. So yeah, let's get right into the lesson. So I'm going to start off by asking, what's a true statement really? Like, what does that mean? Especially in terms of math. Like, when we see the equation 1 plus 1 equals 2, we think, oh yeah, that's true, of course, but what are the grounds for that? What's the grounds for 1 plus 1 equals 2? So it is true if we define 1 plus 2 and, as one of my students pointed out, equals in the usual way, but we could define them in pretty much any way we want. They're sort of just meaningless symbols until we attribute some truth to them. So let's look at another statement and see if it can be evaluated as true/false. The smallest number larger than 0 is 1. Is this true or false? Now, at this point, we'd normally have a discussion time, but we're not in a group of people. You're just sitting at home, presumably, watching this video. So what I'd like to do is ask you to think about it. Is this true? Is the smallest number larger than 0, 1? So now you can think about it. I'll let you pause the video now. All right, now that you've thought about it, we're moving on. Truth is actually relative. It's based on opinion. The answer to this question, it depends on what you're talking about, what area of math you're talking about, what the symbols mean. So relative to the natural numbers, the set of all whole numbers is n, that's what it's called. The answer is obviously 1 is the smallest number larger than 0. So it's true. And this is what n looks like. 0, 1, 2, 3, 4. Blah, blah, blah. So 0 over here is the smallest number in n, and 1 is the smallest number larger than 0. There's nothing in between here. So in n, this is a true statement. But if you consider truth relative to q, the set of all rational numbers, you might have already thought this, or maybe about the real numbers. 0.5 is a number bigger than 0 and smaller than 1. So the statement 1 is the smallest number bigger than 0 is false. And this is what q looks like for reference. So you got 0 here, you got 1 here, you got this whole gigantic load, this arsenal of numbers in between. And that's because q is actually something that mathematicians call a dense poset, but I'm not going to talk about that. Basically, that just means as far as you zoom in, there's always going to be infinitely many things between 2 points. So what's going on here? You'd expect that a mathematical statement like 1 is the smallest number larger than 0 is either true or false, nothing in between, nothing like sometimes true or sometimes false, depending on what you're talking about. And the statement is clearly mathematical, but its truth value depends on something more universal, like whether or not the universe is the natural numbers, or the universe is the real numbers, or the whole numbers, or the rational numbers, natural numbers. You know, it depends on that. It depends on what you're working in. So, congratulations. You just went through the foundational crisis of mathematics. You can look that up if you want. I'm not going to talk about that much here. So, put a pin in that for a bit. We're not going to talk about that anymore in this lesson. So consider the sentence, this sentence is false. Think about that. Do you think that's a mathematical sentence? Is that a mathematical statement, or is it just language being stupid? I'm sure you've all heard of this sentence is false. It's a pretty stupid paradox called the liar's paradox. All right, now that you've thought about it, we've seemed to come across another problem. What did we do to deserve this? Well, the answer is, as you'll see with a lot of model theory, a certain branch of metamathematics, you need to well define this, dumbass, said the universe. So maybe we just need to well define a mathematical sentence, as said by Kurt Gödel. You see, because the problems we've been coming across so far are caused by the fact that we're working in English. We're not working in just mathematical, pure sentences. And we need to define what a mathematical sentence is. A string of characters that satisfies a certain condition that allows it to be sort of grammatically correct. So Kurt Gödel had this idea, but so did Alfred Tarski, Ernst Zermelo, and David Hilbert in unison before they immediately began to race to such a definition, and then Gödel's leg was eaten by Zermelo. So let's try and do just that. What we want to do is make a grammar for what is allowed. So this sentence is false would be fixed, and also presumably that lack of quotation on the right here would be fixed. It doesn't matter what the truth is for grammar. A sentence doesn't need to be true to be grammatically correct. The same is true for math and mathematical sentences. We just want to make it so that you can't say this sentence is false or that sentence is true and that sentence says that sentence is false. Things like that. You don't want to be able to do that. That causes contradictions. It's really stupid. So we want to limit ourselves and sort of create an intuitive set of strings. And we also want to make a sense of truth for those sentences once we're done. So this will fix 1 is the smallest number larger than 0, because this is clearly a grammatically correct mathematical statement, but it doesn't seem to have a truth value that's inherent. So grammar in English doesn't imply anything about truth or validity. It just says what you're even able to express. So my dog is made out of bread is a false statement, hopefully. However, even though it's false, it's grammatically correct in English. So we're going to make something like that for math, something that doesn't have to do with truth, just tells you what you can and can't say. As one of my students pointed out, you could just say blueberries, and that's it. That's all you could say. That would be a valid grammar. That's fine, but it's kind of useless. We want to make a useful grammar. So we don't want to be able to express things about this sentence or that sentence because that just causes loads of problems. That's a requirement that we want to have. And so now try to come up with some sort of grammar, some formal way to say what you can and can't express in math. All right, and now the lesson will end after you have this sort of thought process. That'll be it.